So last week, couple of classes, we sort of introduced the topic and discussed some general points. So starting today, basically, we'll go into the specifics of sort of each of the components of an optical communication system. Starting with the channel, which is optical fiber. Okay, so I mean the JOP students are already aware from the like the optical fiber and the fiber optics course last semester. Many characteristics about optical fibers, right? So many of the concepts might just be recap, and we'll see how some of the parameters, what are the metrics which are important in a communication system. Okay, so just to sort of remind you, and for those who maybe not done an optical fiber course, right? So the optical fiber is made out of glass, and basically it has a core region surrounded by a cladding region, right? You know, so the core has refractive index N1, which is slightly higher than the cladding refractive index N2, right? And the light is guided sort of through total internal reflection, right? So in the ray picture, you can sort of think about rays getting totally reflected. But a more accurate picture is the wave picture, where we solve for the Maxwell's equations, right? In such a structure, and we get some guided modes, right? So basically, for constant refractive index in the core N1 and constant refractive index N2, this is known as step index fiber, right? Because if you look at the index variation, right, so it looks like a step, right? So this is N1 and N2, so there's a step, and the radius of the core region is denoted by A. So 2A is the diameter, right? And so you know that typically the optical fibers have, so we define this quantity delta, which is sort of the difference in the refractive indices normalized to the refractive index. So this is much less than 1 for typical optical fibers, right? And that's sort of an important reason to do this is we'll see, for example, there's a effect known as dispersion, right, which impairs optical communication systems. It leads to broadening of the pulses that we are sending as bits, right? And the dispersion is actually minimized by minimizing this quantity delta. And there are other various reasons why this quantity is much less than 1, which sort of we discussed in the fiber optics course. But for now, basically, you just keep in mind that the optical fibers that are used for communication systems have this property, right? So they're typically step index fibers in most cases. In some special cases, there are some variations. And this quantity, so the refractive index difference, so this is typically like, let's say, 10 to the minus 3 or something. Right, so this is, and both of them are around 1.45, which is the refractive index of glass. So typically, you dope the core region with some atoms like boron or phosphorus to slightly change the refractive index, right? And so there is this quantity defined as a V number, okay, which depends on sort of this core size and this index difference. So it's defined as 2 pi over lambda. Lambda is the wavelength of operation times the core radius times square root of n1 square minus n2 square. Okay, so this quantity square root of n1 square minus n2 square is also known as the numerical aperture. So given a fiber, basically it is characterized by its V number, right? And again, the geography students can recall that basically a lot of the properties of the fiber depend on the V number. So in terms of this quantity delta, if this delta is small, I can also just write this as and hopefully all of you sort of in the beginning I had posted some sections to read which are sort of a refresher of these basics of optical fibers. So hopefully all of you got a chance to go through that and revise some of this. Okay, so for a step index fiber, right? So if this V number is less than this quantity 2.4048, then it's what is known as a single mode fiber, right? So these fibers are known as SMF, single mode fibers, right? And typically nowadays in modern day communication systems, we basically use single mode fibers. We'll see the reasons for that when we discuss dispersion. But yeah, so basically the core size and the index difference, etc., and the wavelength of operation is chosen such that this V number is less than this. Right? So last time we discussed like the telecommunication wavelengths are typically like 1.25 to 1.65 micron, right? So typically the fiber is designed such that for those range of wavelengths, we are in the single mode range. Okay, so the channel characteristics can be sort of divided into two major, or classified into two different classes. Okay, so one are linear characteristics, and as opposed to non-linear characteristics. Okay, so linear characteristics you've already sort of again studied these in the fiber optics course. So the one is attenuation or just loss of the signal on propagation, right? So some propagation loss denoted by this quantity alpha, right? And the second is dispersion. And this effect basically fundamentally is that different frequency components travel at different speeds in the optical fiber, right? Which leads to a broadening of the pulses that we are sending as bits. Okay, and that limits sort of your data rate and leads to intersymbol interference, right? And in addition to this, there are certain non-linear characteristics. Okay, so these might be new to most people. Okay, so there are three sort of broadly three main nonlinear effects which affects signals propagating through right. So okay, maybe this we don't. So attenuation leads to power loss, right? So the amount of power in your bit keeps going down on propagation, right? So this you can imagine that it would limit primarily the distance of transmission, right? So what is the link length will be limited by attenuation, right? Of course, you can compensate it by, for example, putting optical amplifiers. And so dispersion is basically pulse spreading. So this limits, for example, the data rate, you can imagine, because if the pulse spreads, then you can't have the next pulse before a certain time, right? Right, so these are the linear characteristics, and then the non-linear characteristics are sort of three main. One is known as stimulated Brillouin scattering, or SBS. Second is stimulated Raman scattering, or SRS. And then the third is Kerr nonlinearity. So Brillouin, Raman, and Kerr are named after the people who first discovered this effect. Okay, so of course we'll discuss each of these in more detail, but basically, so SBS leads to basically mainly power loss in the signal. So what SBS causes is a back reflection. Okay, so basically you send signal from the transmitter to the receiver, but due to this effect, actually a fraction of the power is back reflected towards the transmitter itself. Okay, so back scattering. And then this Raman effect also sort of leads to power loss in the signal by transferring the power to different other frequencies. Okay, so we are, let's say, sending data at a particular wavelength. Due to this Raman scattering, that power is distributed to different wavelengths. Okay, so the amount of signal in the particular wavelength that I'm interested in, that is lowered. So you can imagine that, for example, if you use a WDM system with many wavelength channels, that can lead to crosstalk between the different channels. Right, and then the Kerr nonlinearity, this is basically due to the fact that the refractive index of the medium becomes intensity dependent. Okay, so we're sending optical pulses with some power. Due to that intensity, optical intensity itself, it modifies the refractive index. Okay, and that leads to various effects like cell phase modulation, cross phase modulation, four-wave mixing. Okay, we'll discuss these things in more detail, but again, they lead to sort of distortion in your signals and crosstalk between different channels. And so, how do we classify these effects into linear and nonlinear? Right. So recall maybe from your basic sort of signals and systems course, like what is a linear system, right? Linear system is something. So any system. So let's say I give it an input some x of t, I get an output y of t, right? A linear system is such that, so for example, if I give x1, I get y1. If I give x2, some other signal, I get y2 of t. So if I give an input which is x1 of t or some linear combination of x1 and x2, I'll get basically the linear combination of the outputs, of the individual outputs. Right, so this is a linear system. Basically, the system is acting individually on each signal, right? And so if you send multiple signals to the system, they all act independently, right? There is no effect of the presence of the other signals on the signal, right? And basically, each of the signals have their own output. So if you send some combination, the outputs are also in that combination. Right. Equivalently, like if you look at the frequency domain, right? So if the input has some spectrum and the output has some spectrum, right? So basically, I can write the output spectrum as some system response, right? Frequency response times the input spectrum. Right. So you can see that the frequency components in the output, there cannot be any new frequency components in the output that are not present in the input. Right, so this is just some multiplication factor, which could be frequency dependent, right? But basically it will just scale the values present at the different frequencies here, but it can't introduce any new frequency component, right? So like if the input signal only exists up to some frequency omega naught and it's zero beyond that, then the output also will be zero beyond omega naught, right? There cannot be any new frequency. Right. A nonlinear system is basically which does not obey this. right? So this is known as the principle of superposition. Right? So a nonlinear system basically, if you send in a linear combination of the inputs, you do not get the linear combination of the outputs. Okay. So again, recall that you can sort of write a linear system time response something like that, right? Right. So it's some linear function of the input. The output is linear function of the input. But for a nonlinear system, the output is a nonlinear function. So here there's not only x but higher powers of x, right? That would be x squared or x cube or something, right? And as soon as you have higher powers of x here, then you can see that this property will not hold, right? So you can just simply see. So for example, if you have y equal to x square, then when you send x1 plus x2, you will get x1 square plus x2 square plus the cross term 2x1 x2, right? So it won't be just the sum of the two outputs. So right, so basically those would be nonlinear systems, right? So basically, attenuation and dispersion fall in this category, whereas these effects fall in the nonlinear, right? So attenuation and dispersion don't introduce any new frequency components in your signal, whereas these effects, because I cannot write it like this now, right? So y of omega can have new frequency components. Again, so if you, for example, take x as some cosine omega t, right? So it has a frequency omega. So when you take the square, right, cosine square omega t, I can write omega t, right? So now you see in the output there is a frequency 2 omega, which was not present in the input. Okay, so these effects introduce new frequency terms, or they cause mixing between different frequency components, right? Which is basically crosstalk. So yeah, I hope this classification into nonlinear and linear is clear. Right. So let's just discuss each of these effects in a little bit more detail and how they impair the signal. Right. So the next few classes will basically be sort of taking each of these effects one by one and discussing sort of their details. Right. So let's start with attenuation. Right. So this is basically propagation loss. Right. So basically, let's say you have some length of fiber. I send in a pulse cut with some optical power at the input. Right. So there is some loss coefficient alpha. So at the output, the amplitude, the amount of power would have decreased. Right. So and the equation of propagation in the fiber with loss, as you know, is that, right? So you get this Beer's law. So e to the minus alpha z dependence, right, of the power. And basically, as we discussed already sort of in the last class, the loss coefficient is characterized in this dB per kilometer units, right, which is right, and it's basically about 2.3 times this alpha in natural units. Okay, so basically this alpha is a function of wavelength, right? And basically, how this varies with wavelength is basically determining what wavelengths that we end up using for optical communication systems, right? This near infrared wavelengths that we are choosing is primarily because this alpha is minimized at those wavelengths, right? So, if you look at the this loss spectrum again, which is sort of briefly looked at already, right, as a function of wavelength. Okay, so overall, the loss decreases with increasing wavelength. Until a certain point where it sort of starts rising. Okay, so if you look at sort of any experimental curve of the loss coefficient of any sort of typical optical fiber that is used, okay, so it will look like this. So there will be some slight variations due to the sort of like fabrication imperfections, but basically it will hug this line, sort of a straight line going down with increasing wavelength. But of course, notice this is log scale, right? So this is like an exponential, almost. I mean, we'll see what the exact dependence of this is, right? Up to sort of this 1.6 micron wavelength, where another effect starts kicking in, and then the loss starts increasing again. Okay, and then there's sort of like a peak here at 1.4. Which we discussed last time, right? That's due to sort of residual moisture content in the fiber. So this is like, and also there's a little peak like around 1.25 or something. Okay, so this line where basically the loss is decreasing with increasing wavelength, this is coming from Rayleigh scattering. Okay, so This is a fundamental effect basically because again optical fiber is made out of glass, and you know glass is an amorphous material, right? Which means there are slight density variations as you go along the fiber. Okay. So there are these tiny pockets where the density is slightly higher, or some pockets where the density is slightly lower. Right? Typically, the size of these pockets are very small compared to, for example, the wavelength. Right? So they're typically in the nanometer size, these density variations, whereas the wavelength here you can see is in micron. Right, so these density variations, which are much smaller than the wavelength, they give rise to a scattering, right? So the medium sort of looks homogeneous, but on a very small scale, it's not homogeneous, right? Contrast this, for example, with a perfectly crystalline solid, where the atoms are exactly placed according to some lattice structure, right? There, basically, the density is, if you have a perfect solid, then the density is constant. There is no variation in the density, right? Whereas for amorphous materials, because you don't have a well-defined crystal structure, right? You have, in some places, the density of the molecules is higher, in other places it's a bit lower, you have some dangling bonds, etc. Of course, this amorphous nature actually helps in the manufacture of the optical fiber, right? You can melt glass and then pull it into these really thin, tiny threads. Right, but any amorphous material also has this fundamental scattering mechanism or Rayleigh scattering. Right, it's the same effect that makes the sky look blue. Right. Uh, so again, you know that the light coming from the sun has the whole spectrum of visible light, but when you look up at the sky away from the sun, we see the sky blue, and that's because of Rayleigh scattering. Right, because this Rayleigh scattering scales with the fourth power of the so if you look at the loss coefficient characterized for Rayleigh scattering, right, that's some constant divided by the fourth power of the wavelength. Right? So smaller the wavelength, higher the loss. Right? So smaller wavelengths are scattered more. So basically, you have light traveling along the optical fiber, it's scattered out of the fiber into this scattering. Right, so it's not an absorption mode, it's just scattering, right? Photons are scattered out of the fiber into sort of out medium outside. It's not that the atoms are absorbing the photons. Right, so this lambda to the fourth dependence is what is shown here. Right, and this constant is about 0.7 to 0.9 dB per kilometer per micron to the fourth. Right, because you have a lambda to the fourth here. Okay, so if you put lambda here at the around 1.55 micron, you get this Rayleigh scattering coefficient to be about 0.16 dB per kilometer. Okay, and you know that so commercial optical fibers have a loss coefficient of about 0.2 dB per kilometer at this telecommunication wavelength. So it's quite close to the fundamental Rayleigh scattering limit. Right? So basically, notice that even if the fiber is perfect, right, there are no defects or impurities or anything in the fiber. Just from the amorphous nature of glass, you get this loss, right? So this is fundamental. You can't overcome this. right? And then this, so if this was the only loss mechanism, then the loss would have just decreased with increasing wavelength. But then there is another effect which sort of scales in the opposite direction, and this is infrared absorption due to sort of photon-phonon scattering, or so basically again you have these molecules, SiO2 molecules, right? And basically they are vibrating, right, at any temperature because of the thermal energy. They're sort of vibrating. So there are phonons present in the medium, right? And these phonons can actually couple to the photons propagating in the medium. Okay, and basically what can happen is that the medium can absorb photons and transfer that energy into phonons. Okay, which leads to this infrared absorption. Okay, and this infrared absorption, as you can see, is increasing with wavelength, right? So the dependence here is something like that. So sort of exponential dependence. Okay. So this is again fundamental to glass. Okay. So the SiO bonds have some modes of vibration, and they couple to photons in a particular manner. So this curve is again fundamental to glass. Okay. So again, just you cannot get rid of this by any means. As long as you're using glass fibers made out of glass, these two loss mechanisms are all present fundamentally, right? And so the best you can do is basically hug these lines, right? So if your fiber is perfect, you'll be like basically along these lines and not below that, right? And as you know, basically, so the commercial optical fibers have some loss profile like this. You can see they're pretty good, right? And as we discussed briefly again last class, that nowadays basically this moisture can also be removed to a much higher degree, such that sort of you cannot even get rid of these peaks, and you are sort of like this, right? So for these so-called dry fibers, basically you are at the fundamental loss limit, right? And if you take both of these loss mechanisms together, one is increasing, one is decreasing, so you get a minima, right? And this minima occurs basically at around 1.55 micron, and the minimum value is about 0.2 dB per kilometer. Okay. There are some other loss mechanisms also, but they sort of lie below, right? So there is also something known as UV absorption. Right. So again, any bonds or any molecule has some absorption lines in the ultraviolet spectrum, right? Because basically these energy levels you have, and they're separated by some energy corresponding to a photon in the UV spectrum, and the tail of that UV absorption sort of comes like this into the visible and infrared region, right? But that typically the value is, you can see, much smaller than the Rayleigh spectrum. Okay, so that's negligible compared to the Rayleigh scattering. And then if you look at, for example, the amount contributed by fabrication imperfections, for example, the fiber not being uniform across the length, or not core not being exactly circular and some impurities in the fiber, some impurity atoms which might absorb at these wavelengths, right? So the fabrication technology has improved so much that these waveguide imperfections lie sort of here, much below 0.1 dB per kilometer. Okay, so you're basically limited by fundamental physics constraints, not by manufacturing or technology constraints. Okay, so there's a question on this IR absorption, right? So we don't need to sort of go into the details, but basically the fundamental mechanism is that, right? So you have these, so glass is silica basically. So you have these SiO bonds, right? And they at any finite temperature. So typically we use these fibers. They're just operating at ambient temperature, right? So room temperature. So basically, you know that there is thermal energy associated with any temperature, PVT, right? So these molecules have this thermal energy, so they're vibrating, right? Which is basically, so these molecules have some vibrational energy, and there are some phonons. Another way of saying in the quantum picture is that there are phonons present in the medium, right? And they have some energy corresponding to this mode of vibration, right? And what can happen is that so light traveling through the fiber, photons, can couple to these vibrations. Okay? So basically you can transfer energy from light, photons, into this vibrational energy or phonons. Okay? So this coupling between photons and phonons is again fundamental, and we'll see that this is sort of related. So for example, some of the nonlinear effects, right? Like Villeneuve scattering or Raman scattering, is also basically this mechanism of coupling of molecular vibration to light. Okay. So this will be present in any medium, right? Depending on the atoms present, basically the wavelength of absorption will change. But anyway, so for glass, it looks like that. Okay? So for infrared wavelengths, it keeps increasing. Yeah, I mean, for our purposes, we don't need any more details into the physics of the mechanism for now. U band, yeah. So you can see that. So the U band is the last band, right? Which was like, I don't know, 1620 to 1670 nanometer or something. So for that, again, you can see that the loss starts increasing, right? So again, if you plot the loss across the bands, the minimum loss occurs around the C band, right? And then L, U here, and this O, E, S or something. So the minimum loss 0.2 is for the C band. Okay. So these dry fibers, what they do is get rid of this moisture peak, and then the whole range here can be below sort of like 0.5 dB per kilometer. Okay. So this is like 1250 to 1975, right? Right. So over this entire band, you can sort of have loss sort of around 0.5 dB or less than 0.5 dB per kilometer. But the minimums occurs around the C band. All right. So okay, yeah. So in terms of loss, basically, modern day fibers are as good as they can be, right? They given the constraints of the material, they have the lowest loss possible, right? And it's pretty good. 0.2 dB per kilometer is much lower than sort of any other medium that we can think of to propagate information. So, yeah. Right, so these dry fibers, so the conventional single mode fiber has some peak here around 1.4 micron. Okay, so this is like so this peak goes above like 1 dB to a few dB per kilometer loss. This is a conventional single mode fiber, and this is sort of a dry or also known as sometimes all wave fiber. Okay, so that's as far as sort of propagation loss is concerned. In addition, just because of sort of how the fibers are packaged, there could be some additional losses, right? So this propagation loss is coming again due to the silica material of the bare fiber, right? And then how, depending on how the fibers are packaged and laid down, there could be some additional losses. Right, so this propagation loss, you can see just scales with length, right? So the total loss would be this alpha in dB per kilometer times the length of the link in kilometer. That would be the total loss in dB. So other kinds of losses that can come into the picture are bending loss. Right, so basically, you can imagine that especially for a long link, that there are various points along the link where the fiber would be bent, right? It won't be perfectly straight. And basically, it turns out that fundamentally, just from solutions to the wave equation, if you have a bent fiber or any bent waveguide, that immediately leads to a loss. So you cannot have a perfectly guided mode in a bent fiber anymore, right? So as soon as you introduce a bend, there is always some loss associated, right? And the loss scales with the radius of curvature of the bend. The tighter you bend, the more the loss. Okay, so this bend loss sort of scales exponentially with this radius of curvature. Okay, so this RC is some constant depending on the fiber parameters, again pore size and numerical aperture. Okay, so again for single mode fibers that are typically used, this RC lies in the range of 0.2 to 0.4 mm. Okay, and if you again put the value here, so if your bend is sort of the curvature is more than 5 mm, typically the bend loss is negligible. Okay, so as long as your bend radius is above a few mm, so let's say a centimeter or more, or 5 millimeter, right? The bend loss becomes small enough that it's negligible compared to the propagation loss. So you can just ensure that the bends that you have along your fiber cable is not very sharp, right? But a bigger problem typically is what is known as micro bending loss. Right, so this is sort of like macro bending loss when if you have just a big bend. But due to fiber cabling, right? So again, I don't know if you guys went through some those initial topics where they discuss how sort of fibers are packaged and right. So you have this core cladding, and then that's packaged into a plastic jacket, which is put into further protection of various kinds. Right. So you have finally have this fiber cables. So when you do all this packaging, you can imagine that basically there could be some sort of areas where sort of the fiber gets stuck, and when you try to push it into some other jacket, there are some small sort of micro bends happening along the length. Okay, so these are very tiny sort of bends happening on a very short length scale. Right, so these can lead to very large losses because the effective radius here is very small. Right, typically let's say microns or less than millimeter scale. So if you're not careful about this, this can like give you like 100 dB per kilometer losses. Of course, the length over which this microbending occurs would only be a few centimeters or maybe few meter up a max, right? But you can see that it can still give you significant loss. So typically these losses scale with the V number. So basically this loss goes down with increasing V number. Okay, so basically you want to operate with as high a V number as possible, right? So we saw that for single mode, we want the V number to be less than 2.4. So the maximum we can go is 2.4, right? So typically, if you look at the commercial fibers, their V numbers are typically between 2 and 2.4 for the wavelength range, for the telecom wavelength. So like 1.3 to 1.6 micron, the V number is in that range, close to the single mode cutoff. The cutoff wavelength is typically less than 1.3, so like 1200, 1250. Okay, and then there could be losses when you try to join two pieces of fiber or like two different links you want to join at some point, or like you want to connect some equipment like an optical amplifier or a laser or a detector or something, right? So you have to connect a fiber to another fiber or some other connector. So there are two types of joints. One is a splice, where basically it's a fiber to fiber connection, right? So basically a bare fiber. So you have two bare fibers on either side, and then they sort of fuse together using what is known as a fusion splicer. Okay? So basically you align these two fibers next to each other, and then you have an arc which basically melts the glass and then fuses the two pieces together. Okay. And again, the splice loss then depends on, for example, this alignment. For example, we had discussed this in the fiber optic frame. But basically, typically, the splice loss typically with the modern fusion splicers, typically for each splice you have only 0.1 dB loss. So if you're a slightly bad splicer, then it can go up to maybe 0.3, 0.4, but typically much less than 0.5 dB. And for the best ones, you can get about 0.1 dB for each splice, right? But again, for a very long link, you will have these splices coming in at various points, right? So for example, either you're trying to combine two different routes together, or you're trying to put in some optical amplifier or some other equipment here, you want to splice into the main line, right? So that's splice loss. And then for fibers which are connectorized, so right, which are already packaged and then have this connector which you can plug into, for example, a laser or a detector, or even connect to another fiber. So you have fiber connectors which you can sort of screw in fibers with these connectors, right? So that is also not perfect, right? So that gives you what is known as connector loss. And typical connector loss is about like 0.5 dB. So it can lie between, let's say, 0.3 to 1 dB. Okay, so the connector loss is typically larger than the splice loss, right? But of course, splicing is more complicated, right? You have to strip the fiber to its bare glass and then fuse it together. Whereas connector, like you can remain in the package and then just screw in two fibers to connect. So this is much easier to use, but slightly higher loss than the splice. Okay, so basically for a long link, let's say of hundreds or 1,000 kilometers, you need to take into account all these losses occurring along the link, right? So propagation loss, and then these other bending losses and splice and connector losses at various points to sort of calculate what is the total loss in your link, right? And to compensate for these losses for long links, right? For once you go beyond hundreds of kilometers, you need optical amplifiers, roughly like every 100 kilometers or so, to boost the signal again.
Excuse me, sir.
Yeah.
Sir, why this microbending loss decreases with increase in V number?
V number basically gives you an idea about how much the light is confined in the core of the fiber. Okay, so um, right. So again, so imagine this fiber. You have a core region in the middle, right? And then you have some mode here, optical mode. So you have some intensity or field profile, which is so most of the power is in the core, but there is some power which leaks into the cladding, right? And then basically because of the bend, this power in the wings is leaking out. Okay, that is what is giving you loss. So as V number increases, basically the percentage of the power in the core goes up. Okay, so the power leaking into the cladding is smaller. So you can think of it like this. So V number as we saw, so it's scales with the core size, right? So higher V number you can think of as a higher, so A over lambda, right? The core size divided by the wavelength of operation, that's higher for a higher V number, right? And so you can see that a higher core size would mean that more of the power is confined into the core, right? So if less field is leaking out into the cladding, there is less power which can leak out as because of the wind, right? So that's like a qualitative understanding that one can get.
Yes, sir. Thank you, sir.
Okay, so yeah, that's all about attenuation. Yeah, I hope clear. If there are no other questions on attenuation, then we can just go to dispersion now. Right. So right. So what is dispersion? Again, so let's say we are sending some optical pulses at the transmitter. Right. Then we have this fiber, and at the output, after propagation, basically these pulses start broadening out. Okay. So we start broadening, and if they broaden enough, then basically neighboring pulses can start interfering with each other. Okay, and then you can see that you lose your sort of signal. So it limits your data rate. You need some minimum separation between the bits to reconstruct the data. Right, so this overlapping between neighboring bits is known as intersymbol interference, or ISI. So again, this is sort of some recap from the fiber optics course. So there's various mechanisms of dispersion depending on the type of fiber used. Right, so the first one is intermodal dispersion. So this is the dominant dispersion mechanism if you use a multi-mode fiber. Right, so this V number, if it's large, right, if it's not less than 2.4 but some larger number, then you have more than one mode. Right? So the first generation of optical communication systems, when the technology to make nice single mode fibers was not figured out, the first generation of links used multi-mode fibers, where so sort of in the 70s and 80s, so the dominant dispersion mechanism was intermodal. Right, these different modes in the fiber have different group velocities, so they travel at different speeds. Okay, so at the input, when you excite, you are exciting all these different modes, right? And all of them travel at different speeds, and at the receiver arrive at different times, which leads to spread. Okay, so this is for multi-mode fibers only. So nowadays this is not an issue because, as I said, mostly we use single mode fibers. But again, for some short links, like for example now inside data servers between racks, people want to communicate using fibers, then one could still use like multi-mode fibers for very short links, like meter scale or less than kilometer. And once you go to single mode fibers, then you have intramodal dispersion. So there's only one mode, but you could still have dispersion within that mode, right? And that is also known as chromatic dispersion or group velocity dispersion. Right? Or GVD for short. Right, so as the name suggests here, chromatic means frequency, right? Color. So this dispersion mechanism is basically that different frequency components within the mode are traveling at different group velocities. Right, so intermodal means different modes or different spatial profiles, right? Or equivalently different rays in the fiber are traveling at different or taking different times, right? Whereas here you have only one mode, but the different frequency components within that mode are traveling at different speeds. Okay. So then basically the effect is similar. The different frequency components arrive at different times, and that leads to a spread. Okay, but the magnitude of this intermodal is much bigger than the intramodal. Right? So for multimode fibers, this is dominant. And again, you know that, for those who've done the fiber optics course, this is again has two contributions. One is from the material, right? So any material you take, like glass, the refractive index is wavelength dependent, right? And you know that group velocity depends on the index, right? So if the index depends on wavelength, then the group velocity will depend on wavelength or frequency, leading to dispersion. Right? And the other is waveguide dispersion. So this comes just from the waveguiding effect, the fact that you are confining mode in this optical fiber medium, right? Just due to the waveguiding effect, there is a dispersion. So you can think of this as again. So if you look at a mode, right? So the core has some refractive index n1, the cladding has n2, and you have a mode which has a certain fraction of the power in the core and certain fraction in the cladding. So you might recall this concept of effective index for a mode, right? That lies between n1 and n2, right? That basically is a measure of how much of the mode is in the core and how much is in the cladding, right? If more of the mode is in the core, then n effective is closer to n1. If it leaks out more, then it goes closer to n2. Right. So now imagine a situation where you have no material dispersion, right? So n1 and n2 are constants, right? There is no dependence on wavelength. But now I change the wavelength, right? You know again from fundamentals of optical waveguiding, right? That this mode profile, right? For each different wavelength, we solve the wave equation. So for each different wavelength, we get a slightly different mode profile. Right? Even though n1 and n2 are constant, when we change the wavelength, the mode profile changes slightly. Right? So this factor, confinement factor of how much power is in the core and how much is in the cladding, that changes slightly. Right? Or in other words, this n effective is a function of wavelength, even if n1 and n2 are taken as constants, not a function of wavelength. Right? So this is just an effect of the waveguiding, that the mode profile is changing with wavelength, even though the material refractive index is taken to be constant, right? And now, if this effective index is a function of wavelength, again, the group velocity or the energy carried by this mode will depend on the group velocity, which depends on this index, which is now a function of wavelength. Okay? So, again, it will lead to a dispersion. So typically we'll see that this contribution is typically larger in optical fibers than this, and that's true typically in most waveguides. The material contribution is typically dominant over the waveguide, but you can change the profile, like the dispersion profile with wavelength using this waveguide dispersion. We'll see how we can do that. Okay. So, and again, so this is chromatic dispersion, which depends on the frequency components, right? So it depends on the also on the source. So that your transmitter, right? So this is like, for example, it could be an LED or a laser, right? And it gives out some spectrum, right? So the light coming out of this transmitter has some spectrum, so there is a spectral width here in wavelength or frequency, right? And you know, for example, that LED, the spectral width is much larger than a laser, right? So for a laser, it looks more like that. And basically, you can see the fundamental effect here is that different frequency components or different wavelengths are traveling at different speeds, right? So now if you have a larger spread in your wavelengths, then you can imagine that will lead to more spreading, right? Because now you have a bigger range of wavelengths, they are all traveling at different speeds. Here, basically, almost all the wavelengths are the same, or like there's basically only one wavelength, or the spreading wavelength is very small. So then you can see, again, imagine that the spreading would be much smaller, right? So this group velocity dispersion depends on the source bandwidth also. We'll see the explicit dependence, right? The sort of the relevant quantities. So let's say we are sending some pulses of duration tau p, right? So that will be, for example, related to my data rate, right? So the data rate will be proportional to this tau p. The smaller I can make tau p, the higher data rates I can operate at, right? But this tau p broadens due to propagation in the fiber, right? So at the output, like this is now tau p plus some delta tau. So for LEDs, basically this spectral width. So if I look at it in terms of frequency, so delta omega, that is much bigger than the inverse pulse width, right? So there's a bandwidth defined just by the pulse rate here, right? Which you can again roughly sort of imagine as the data rate, right? 1 over tau p. So for incoherent sources like LEDs, the spectral width of the source would be much bigger than the sort of the data rate or the inverse pulse width. Whereas for lasers, we are sort of in the opposite region, right? So it's almost like a single frequency. So the spectral width is negligible, and the frequency components in your signal are just coming from the sort of mathematical fact of that as soon as you have a pulse in time, that automatically means that you have some finite spread in frequency, right? So if you take the Fourier transform of this pulse, in the frequency space you get a spread which is 1 over tau. So anyway, so we'll see basically the dispersion is limited by, so if you're using lasers with like a single frequency, then the dispersion would depend on sort of your pulse width. But whereas if you use incoherent sources like LEDs, the dispersion would be determined by the spectral width of the source and will be sort of independent of the pulse width. Okay, and then there is another sort of dispersion mechanism which is known as polarization mode dispersion, PMD. And this is sort of fundamentally different effect is coming from, as the name suggests, the polarization. Okay, and this is coming from the fact that so you can see that if the fiber is perfectly circular, then these two polarizations, like vertical and horizontal, so the mode can be treated as linearly polarized modes in this limit of small index contrast. So they can, for example, either be vertically polarized or horizontally polarized. And if it's a perfect circle, then these two would be degenerate modes. So all their properties will be the same and they will travel at the same speed. But what happens is that for a long fiber, along the length, this doesn't remain a perfect circle just due to manufacturing imperfections. So at some points it's sort of elongated. It looks like an ellipse in the horizontal direction. And at some other place, it looks like an ellipse in the vertical direction. In some other place, it's elongated in some other direction. So you have these variations in the core, right? And that breaks the symmetry between these two polarizations. So in certain sections of the fiber, like one of these travels faster than the other, right? So basically, your input signal, which is now composed of, in general, both these polarizations, right? Because of these fluctuations in the sort of speed of the two orthogonal polarizations, that also leads to some throttling. Okay, so these are sort of the mechanisms by which dispersion happens, right? So again, we'll quickly go through each of these, and the most important is basically this chromatic output velocity dispersion, because modern day links we use only single mode fibers, so we don't have intermodal, right? And typically the polarization mode dispersion is much smaller than the group velocity. Okay. But yeah, we'll quickly discuss sort of each of these. So intermodal, you can think of, so it's a multi-mode fiber, right? You can think of different modes as different rays propagating in the fiber, right? So for example, you could have a ray which just goes straight through, right? So this represents the core region. So this is the core radius A, right? So at the input, I launch, let's say my light source launches rays at all different angles, right? So the ray which takes the shortest path would be the one that goes straight through. Rays which go at an angle, of course, take longer paths, right? And so now, depending on this angle theta, right? So the maximum angle that one can have is that such that this angle here, right? This is the critical angle, right? So basically, you need total internal reflection at this interface. So angles higher than this will leak out into the cladding. So the maximum angle here can be when this angle of incidence at the core cladding interface is the critical angle, theta. So the longest path will be taken by this ray which makes the critical angle, right? So that takes the longest time, this takes the shortest time. And you can easily check that, so if this is x, right, this hypotenuse here is x over sine theta c, right? So if this whole length is L here, then this length here will be L over sine. Okay. So the minimum time is L over C over N1, right? So C over N1 is the speed. The maximum time is the maximum path, which is L over sine theta C divided by C over N. Right? And the spreading in the pulse delta T. So will be the difference in these arrival times. Right, and you know the critical angle is defined like this. Right, that's the definition of the critical angle. So plug this in here. get that. Right, so this is basically just delta, the normalized refractive index difference. So you can see that the dispersion, which is defined as the broadening per unit length, delta T over L, goes as the core refractive index times delta, this normalized index difference divided by speed of light. Right, so you can see that. So here straight away it tells you that the dispersion. So here, what are the units of dispersion? Delta T is units of time, right? Second. And this is length, so second per meter. Right? It directly scales with the index difference delta. So you can directly see that why we need small index difference. So again, recall that the figure of merit that we typically look at for these links is basically the data rate times the distance over which you can send the information, right? So if you have a pulse which is spread by delta t, then you know that the bit rate, right? So the bit period has to be more than the spread, right? So that the neighboring pulse doesn't interfere. So if you look at the bit rate, which is 1 over TB, so if TB is greater than delta t, then 1 over TB is less than 1 over delta t, right? So this bit rate times the link length is less than L over delta t, right? And from here, so bit rate times length is less than that. Okay. So this figure of merit of the bit rate times the link length is limited by this quantity, which scales as 1 over delta. Right? So that's why smaller delta helps you increase the data rate or the link length. So if you take a look at typical multimode fiber, this core index is about 1.5, delta is about 0.01. Okay, so if you plug in the numbers here, so you are limited to about 20 megabit per second kilometer. Okay, which means that if you have a link length of 1 kilometer, the maximum data rate you can operate at is 20 megabit per second. If your link length is 10 kilometers, then the maximum data rate is 2 megabit per second. Okay, so you can see that these numbers are quite low by modern standards. But like sort of the first generation of optical systems were operating in this region, with multimode fibers. Okay, I mean, if you look at the dispersion value here for these numbers, that is just inverse of this. That's about 50 nanosecond per kilometer. Right. So basically, if I send a pulse after propagating 1 kilometer, the pulse broadens by about 50 nanoseconds. Right. So, I mean, you know that this is quite bad by modern standards. Right. So that's why we moved to single mode fibers, where now we eliminated intermodal dispersion and now are limited just by chromatic or velocity dispersion. So we'll look at that in more detail in the next class.